Hello. In this video, we're going to tackle trig integrals. Now, trig integrals are basically similar to integration by parts in that there's multiplication inside the integrand. But instead of between functions of a different type, like an exponential and a trig, or an algebraic and an inverse trig, instead, what we have is the multiplication of two trig integrals. And by trig, we mean the basic six: sine, cosine, tangent, secant, cosecant, cotangent. So we've got this multiplication between trig integrals, and we want to know how to integrate these. Now, the good news is there is a pattern that repeats throughout this entire process where we basically use the Pythagorean identities in order to reduce the integral into something that can be integrated directly with the antiderivative, or that we can use u substitution on. The bad news is there are so many different possibilities and cases that it can be overwhelming. So I have a handout for you that you can use to do this, and you'll find that the handout is actually contained within my lecture notes. So I've broken it up into pieces. We're going to tackle these in two videos. We're going to deal with products of sine and cosine of various powers first, and then in the next video, we'll deal with products of tangent and secant. Now you may say, well, what about cotangent and cosecant? They're out there too. Well, it turns out that you can use the rules for tangent and secant just by converting the tangent to cotangent and secant to cosecant. So we'll be covering all six, but we won't be covering all possibilities. We're just going to be covering the ones for which there are techniques. So again, that would be products of sine and cosine, and products of tangent and secant. So in this first video, we're going to tackle products of sine and cosine. Now, again, what I have said is that we are going to use the Pythagorean identities in order to reduce these integrals with their complicated product integrands into something we can use u substitution on, or that we can integrate directly. This does not mean, however, that you will not need integration by parts. When we get to the tangent and secant ones especially, you'll find that there is a case there where integration by parts is required, and they become quite complicated and long. They're kind of nightmares, and I don't know what else to say. This stuff is hard. Calculus 2 is the hardest of all the calculus courses. There just really is no easy section. So what we want to start with here are the Pythagorean identities. So hopefully you do remember what the Pythagorean identities are. And let me go ahead and start sharing my screen with you so that you have a better shot of what I'm looking at. If I can get my cursor to come over here, and I'll share my screen. Okay, so now what you see on your screen with me off in the corner is the Pythagorean trig identities. Now, you should already know these. You should have memorized them, but if you haven't, now's your opportunity. You need to know them. You have to have them memorized. You just don't have time to go look up everything. I mean, let's face it, you can't use a dictionary to spell the word that or what or who. It's just ridiculous to use a dictionary for a 3 or 4 letter word. Well, it's ridiculous to have to go look up at that Pythagorean identity. So get them memorized. I recommend that you start with sine squared plus cosine squared equal 1. That's really the only one you need to memorize. And you probably already know it, even if you don't think of it that way. Remember that when we're looking at the unit circle and we draw a triangle coming from the center of the circle out to the edge of the circle, we can drop a line vertical down perpendicular to the x-axis, and then the radius connects out to that point on the circle. And then we also have a segment of that triangle that lays along the x-axis. So we basically have something parallel to y and parallel to x, which makes it a right triangle where we can use the Pythagorean identity. Now, when we look at this, we can also see that the cosine of that angle becomes the x-coordinate, and the sine of the angle becomes the y-coordinate. So basically what you have here is y squared plus x squared equals 1, or you can reverse the order and make it x squared plus y squared equal 1 if you like that better. So basically you really already know this one. This one you've got to have memorized. Once you have that, then you can find the second two very easily. To find the second one, take the original sine squared plus cosine squared equal 1 and divide all three terms by cosine squared. Sine over cosine gives you tangent, so you have tangent squared plus 1 equal to secant squared. This is the second Pythagorean identity. I'll be honest with you. I kind of have them all memorized by the time I'm done doing this section, and then it sort of floats away again, and all I know is sine squared plus cosine squared equal 1. But I know how to derive them, which means that I can always find them no matter what. So first one, or second one, is to divide everything by cosine squared. Then you start back at the original, sine squared plus cosine squared equal 1, and you divide all three terms again, but this time by sine squared. And that gives you the third Pythagorean identity, 1 plus cotangent squared equals cosecant squared. Now, the ones we'll be relying on the most often will be the first two. We're not really going to take a lot of look at the ones involving cotangent and cosecant. They're similar, like I said earlier, to tangent and secant. So if we learn tangent and secant, in essence, we're learning cotangent and cosecant, but with tangent and secant, we don't have to worry about the negative and the derivative, which makes our life a little easier. Okay, so here are the basic three trig identities right here in the center of the screen. Sine squared plus cosine squared equal 1, tangent squared plus 1 equals secant squared. These two are our best ones for trig identities. And the third, 1 plus cotangent squared equals cosecant squared. Now, once we have these, we're ready to go. We're going to start with products of sine and cosine. They're the easier of the trig integrals. I did not say easy, and I don't mean easy. There's not an easy topic in calculus 2. There's just not. They're all hard. It's just the easiest of a hard group, all right? So when you're doing these, you also need to be aware that sometimes there's more than one way to integrate. And when you integrate in a different pattern than, say, your classmate, then you may get a different answer, what looks like a different answer, but is in fact equivalent. So how do you know it's equivalent? Graphing is not a way to look at two functions and decide if they're the same. You can never see the entire graph. So graphing is a terrible way to determine if two functions are equivalent. Instead, use a graphing calculator or some kind of online graphing utility like Desmos or GeoGebra. Take one of the functions and divide by the other. You get 1 or something that's practically 1, like 0.00000000597, as close as the graphing calculator can get. If it's practically 1 by division, then you know they're probably the same. The other thing you can do is subtract one function from the other. You essentially get 0 or something super, super close to 0. Oops, I think I said these backwards. This one should be 1.000000495 or 0.999999872, and this one should be close to 0. This is two ways of determining if two functions, which look different, are in fact equivalent. And this does happen quite a bit with sine and cosine. And I'll point out when we get to those ones where it can be done in more than one way, where you might get different answers that in fact are equivalent. Now, it's my job, of course, as the professor to know, no matter how you solve it, that the answers are equivalent. As a student, it's a little bit luckier. You just solve the problem. You don't have to worry about if your answer is equivalent to mine. That's my job. Okay, so let's start with the basics. I've divided it up. You can see over here in the left navigation pane that I've divided it up into part 1, which basically is dealing with sine and cosine products in the integrand. In there, we have basically 3 cases, case 1, case 2, case 3. And each of those cases may have types. Remember, I said there is a basic underlying strategy, which is use the Pythagorean identities to reduce the integrand to something you can integrate directly or use U substitution on. But there are many different types, and this one you might use this Pythagorean identity, and this one you use that Pythagorean identity. And that's what makes so many different cases. Okay, let's start with part 1. Now, when we're looking at part 1, we have trig integrals, products of sine and cosine. Our part 2 is going to be the products of secant and tangent. So we have sine to some power of x, cosine to some power of x. Notice that the arguments to the trig functions are identical. They're the same. If it's sine to the fifth power of 2x, then the argument to cosine also needs to be 2x, not something different like 3x or 5x or 11x or even x. They need to have the same argument. We will talk briefly about what to do if they don't. That would be in case 3. So again, looking over here off to the side, when you're looking at the left navigation pane, you'll see that case 3 has a case where they're not the same argument. So what do? Now we have 3 cases to consider. We know that case 3 is going to involve something where the arguments may not be the same. So now we're looking right here at case 1. At least one of the powers on either sine or cosine is a positive odd integer bigger than 1. So at least one of them is 3, 5, 7, 9, 11, 13, odd and bigger than 1. All right? So it's odd and bigger than 1. Now there are 3 possibilities here: that it's the power on sine that's odd, bigger than 1, or it's the power on cosine that's odd, bigger than 1, or both of them have an odd power bigger than 1. It could be sine cubed of x, cosine cubed of x, or sine cubed of x, cosine to the fifth of x, right? But it could also be cosine cubed of x, sine squared of x, or sine to the fifth of x, cosine to the fourth of x. All I need is one at least of the powers to be an odd integer bigger than 1. Now, what's our strategy? The strategy is here in the middle of this first paragraph. We're going to take the 1, or one of the ones, if they're both odd bigger than 1. We're going to choose one of them that is an odd power greater than 1, and we're going to pull one of the trig functions off. So let's say we have sine cubed. So basically you have 3. We're going to pull one of the 3 off so that what we have is sine squared times sine. Now, again, if you put them together, it makes sine cubed, but we're going to split them up. So we're going to make, out of the odd power greater than 1, we're going to pull 1 away by itself. And then what's left over here is going to have to be even. If it started odd and you pull 1 off, what's left has to be even. If it had been sine to the fifth, when you pull 1 off over here, you get 4 left, which is still even. So that's going to be our strategy. We're going to take one of the ones that has an odd power greater than 1. We're going to pull 1, exactly 1 away, so that what's left is an even power. Then we're going to use the Pythagorean identity, and we're going to replace the even powered factors using the Pythagorean identity, sine squared plus cosine squared equal 1. So let's take a look at the different types here. So these are basically the 3 different possible cases of what we've got going on here. So what I've started with here is that n is a positive odd integer greater than 1. That's the power on cosine. And m, the power on sine, could be anything. It could be even, or it could be odd. But we're going to focus on the power on cosine being the one we're paying attention to. And it's an odd power, and it's bigger than 1. So 3, 5, 7, 9, 11, 13, 15, whatever. Now we take this power on cosine, we pull 1 cosine off. So now we have cosine to an even power times cosine of x. Now, what does that give us in our integral? Then that gives us sine to any power of x, and I'm just keeping the argument simple x, times cosine to an even power times cosine. Remember, I had an odd number of cosines, and I pulled 1 away, so I got an even group and the 1 by itself. Now I'm going to take the even ones, and I'm going to convert them in pairs, each pair, using the Pythagorean identity. Now, the Pythagorean identity that we want is this one right here, sine squared plus cosine squared equal 1, but we want to solve for cosine squared, which is this right here. So we want to use the form of it that says cosine squared of theta, or x, is equal to 1 minus sine squared. Okay, so I'm going to take each pair of these even number of cosines, and I'm going to replace them with 1 minus sine squared. So what if I had 4 cosines there? Then I've got 2 pair, and each pair will give me a 1 minus sine squared, which will give me a group 1 minus sine squared quantity squared. All right. So for each one, I get a 1 minus sine squared. So this will give me cosine to the n minus 1 x pairs with factors of 1 minus sine squared. All right. So now that you see what I've got right there, then we'll do a trig substitution. So u is going to be sine of theta or sine x, depending on what the independent variable is. And the derivative of u is that one cosine that you pulled off the odd numbers. Remember, you split it into an even group times 1 by itself. That 1 by itself becomes part of du. So du is cosine of theta d theta, or cosine of x dx. All right, so this is basically reducing it into something where we can use u substitution. Now what we want to do is take a look at an example. So we have the example for us right here, which is cosine to the fifth of x, sine of x dx. So let's take a look at what we want to do. When we're looking at this and we're analyzing it, first we start with, well, what do we have in the integrand? Well, we have a product of two trig functions. I can't do IBP because they're two different trig functions. They're the same type of function. IBP works on two different types of functions, algebraic and logarithmic, inverse trig and exponential. They don't have the same type. Even if it's just natural log, it's natural log times 1, which is algebraic. So it's really algebraic and natural log. So we've got the same type and we've got multiplication. The arguments are identical. Notice that the power on cosine is odd. It's 5 greater than 1. And we don't care then about what the power is on sine. So what we're going to do is we're going to take this one right here and we're going to pull off one of the cosines. So we have cosine to the fourth of x times cosine of x times sine of x dx. So I've taken the fifth power and I've pulled it apart into two different factors. Now I've got, in essence, two pairs of cosine squared. So I've got here a cosine, oops, my pen's not writing, cosine squared of x, cosine squared of x, or you can think of it as cosine squared of x squared, if you want to think of it that way. So when I'm looking at this, the next thing I want to do is I want to convert the even group using the Pythagorean identity. So remember, we can come over here to the side. Maybe let's use a different color for our scratch work. We have sine squared of, and our argument is x, plus cosine squared of x equal 1. So cosine squared of x equals 1 minus sine squared of x. So then we do a substitution. So this gives me the integral of 1 minus sine squared of x, quantity squared, times cosine of x, times sine of x, times dx. Right? Now you may be thinking, yeah, but that's worse, right? You took something that looked not too awful and now you've made it into something even more complicated. Yes, but now I can do u substitution. So what I'm going to do now is I'm going to choose my u appropriately. My one that I pulled off is going to be part of du. So my u is going to be sine of x, and my du, abusing the notation and swinging the dx around, is going to be cosine of x dx. So this part right here becomes du. And then I can rewrite what I have in the integral. This becomes the integral of 1 minus u squared times sine of x, which is u, times du, which is the cosine of x dx. Well, now this is simpler, right? This becomes something that's in essence polynomial in behavior. Why don't you just be able to use the power rule for integration on that? So go ahead and pause the video here, work out what the answer should be, and then come back when you've got an answer and compare it to mine. So how'd you do? Let's see what we've got. So the first thing I did is I left some vertical space so I could multiply this out here. This is a binomial square. Make sure you multiply it out appropriately. Don't lose the middle term. That's a basic algebra error and a big no-no in my class. Then you distribute the u and you come up with this polynomial expression in u. And then you can integrate it using the power rule for integration. And then back substitute that u is sine of x. So you get 1/6 sine to the 6th of x minus 1/2 sine to the 4th of x plus 1/2 sine squared of x plus the constant because it was an indefinite integral. We're getting an antiderivative function. Hopefully this makes sense to you. I did provide answers inside of the notes if you have a copy of my notes, so you can check it down here. All right. Now let's take a look coming down to the next one. When we're looking at the next one right here, making sure, yes, there we go. Let's make sure that we're ready to move on to the next one. If you need to pause the video and review, go ahead and do that. But if you're ready to move on, we'll take a look at type 2. So in type 1, we were focused on cosine having the odd power greater than 1. So 3, 5, 7, 9, 11, etc. This time, what we're going to do is we're going to focus on sine having that power greater than 1, which is in essence going to be exactly the same process. We're going to be doing the same thing, but for sine instead of cosine. So yeah, they're different types, but the strategy is the same. All right, the strategy is going to be the same. So what are we going to do? This is just like type 1. Since the power on sine is an odd number, let's say there's 7, all right, we'll do 7 this time. Pull one of the sine of x's off. So you've got 6 over here and then the 1 by itself over there. 7 was probably not a good choice. I need 3 hands, all right? So then you have an even number of sines, 6 of them, times the odd one out, that's the 7th. That 7th one is going to become a part of du. You're going to take the 6 even powers of sine and you're going to convert them in pairs. If you've got 6, then you've in essence got 3 pairs of sine squared, which you can convert with the Pythagorean identity sine squared plus cosine squared equal 1. So sine squared equals 1 minus cosine squared, which you'll see down here at the bottom of the page, right here. So we're going to replace all those even ones, and then we'll in essence be done. Now, we'll use u substitution again, but this time u will be the other trig function, cosine, because we're going to convert all of our even sines into cosines. So cosine will be the main trig function, so it becomes u. Our du will have to have a negative in it because the derivative of cosine is negative sine of x dx. But as long as you're careful with the negative, it should work out okay. And then you complete the integration with u. So type 1 and type 2 are essentially the same, all right? So you're using the Pythagorean identity, you're taking the one with an odd power greater than 1, you're pulling 1 away, converting the even pairs left behind using the Pythagorean identity, and then doing a trig substitution or doing a u substitution. The third type is what if they're both odd? Now, if they're both odd, you're going to choose one of the trig functions. Either one will work, it won't matter. But this is one of those cases where your answers will look different. So let's say that you have sine to the 3rd power and cosine to the 5th power. And you choose to convert the sine cubed into sine squared times sine. So you're going to convert sine squared into the cosines using the Pythagorean identity. But your classmate goes for the cosine to the 5th. And he makes cosine to the 5th into cosine to the 4th times cosine. Well, he's going to convert his cosine to the 4th into sines. You're going to get answers that look fundamentally different, but are in fact the same. This is when you would use your graphing calculator or your graphing utility, divide one function by the other and see if you get something essentially 1, or subtract one function from the other and see if you get essentially the 0 function, right? And then you know that they're actually equivalent. So let's take a look at this one right here as an example. We have sine cubed of theta, cosine cubed of theta. And again, it could be x. I just use theta, no particular reason. But at any rate, let's take a look now and see what we've got on this particular one. So let's work this one. I'm trying to leave it so that there's enough space in the bottom. And I'm going to actually work it 2 times. So I'm going to put a bar coming down the middle. I don't know how, oops, I think I just erased my bar. I don't know how far I'll need to go, but we'll make it about that far. And I'm going to work it using both strategies. So I'll work it first using maybe sine, pulling apart the sine, and then I'll work it with cosine or vice versa. Okay, so let's take a look at sine to the cubed of theta, cosine cubed of theta. The powers on the trig functions are both odd greater than 1. So just pick one. Doesn't matter. It'll work either way. So we're going to pick one. So the first one I'm going to do is I'm going to do sine squared of theta, round out my theta, times sine of theta, times cosine cubed of theta, d theta. So I chose to go after the sines. So I pull one sine off. That leaves an even number. Now I'm going to use my Pythagorean identity. So I have sine squared of theta plus cosine squared of theta equal 1, which means that sine squared of theta equals 1 minus cosine squared of theta. So then I can replace this. This becomes the integral of 1 minus cosine squared of theta times sine of theta times cosine cubed of theta d theta. Now you may think, eesh, that looks bad, right? No, it's really actually not. It's actually good. We're very close. We just need to do the u substitution. Because I broke down sine, the other trig function becomes my u. So u becomes cosine of theta, and du becomes negative sine of theta d theta. And then I can replace that inside of my integral. So I get 1 minus u squared, and I'm going to move the sine of theta to the end. And then I have cosine cubed, which becomes u cubed. And then sine of theta d theta isn't quite du. I need a negative on it. So sine theta d theta is negative du. So I can put that in like that, negative du. Now the negative needs to float to the front. And then I can multiply out the 1 minus u squared times u cubed. I could pull the negative on the front of this, which kind of appeals to me. So I have a negative 1 minus u squared times u cubed times du. The negative multiplied across there, and I kind of like the u cubed at the front. And that gives me u squared minus 1 du. It's looking much better. I like this algebra. And then I can distribute it using the distributive property. And remember, when the bases are the same and you're multiplying, you add the powers. Don't give me u to the 6th. And so that gives me u to the 5th minus u cubed du, which becomes, of course, 1/6 u to the 6th minus 1/4 u to the 4th plus a constant. And then I go back, substitute. U is cosine. So I have cosine to the 6th of theta with a 1/6 minus 1/4 cosine to the 4th of theta plus a constant, right? Checking my notes, make sure I haven't made a mistake. Okay, pretty basic. Basic strategy is the same as what we did there in type 1 and type 2. We just chose sine to break down. Now let's go back to the original and let's say, well, they were both odd, so you could have chosen cosine to break down instead. So let's break down cosine. And this time I'll use a different color to kind of contrast, make sure you don't get confused. This time, if I'm going to break down cosine, I'm going to end up with sine cubed of theta times cosine squared of theta times cosine theta d theta. Remember, we're pulling off 1 because we want what's left to be an even number so that we can use a Pythagorean identity substitution. Now this time I need to substitute for cosine squared. So cosine squared of theta is equal to 1 minus sine squared of theta. And that's coming from the Pythagorean identity. So this becomes the integral of sine cubed of theta times 1 minus sine squared of theta times cosine of theta d theta. Now, some students just go ahead and work with the trig functions. I find it, well, kind of onerous to do the trig functions. I like to use u substitution and get rid of the trig functions. It's just less writing and I'm less likely to make a mistake. So I'm going to make a substitution here. Since sine is now my primary trig function, u is sine of theta and du is cosine of theta d theta, which of course is this part here at the back. And so this then becomes, when I integrate, I get u cubed times 1 minus u squared times du. Now I can go ahead and multiply that out. it looks similar to what was on the left, but it is not the same. So be careful about this. They're not going to be exactly the same. Similar, but not the same. So this is going to give me the integral of u cubed minus u to the fifth. Add the powers when you're multiplying the same base. And then this gives me 1/4 u to the fourth minus 1/6 u to the sixth plus a constant. Back substitute for sine, and we get 1/4 sine to the fourth of theta minus 1/6 sine to the sixth of theta plus a constant. Okay, let's check our answer with the notes, make sure I haven't messed up somewhere. Okay, these are not the same, right? Don't freak out. It's fine. This does not look like this. But if you spent half an hour or an hour with a bunch of Pythagorean identities and trig functions, you could turn one of these into the other. This is where you want to take your graphing calculator, your graphing utility, and take one of these functions in parentheses and divide by the other function in parentheses and see if the graph or the function value is essentially 1. If it is essentially 1, you know they're identical. If you take this one and you subtract this one or reverse the order and you get essentially 0, then you know that they are essentially the same function. That tells you they're equivalent answers. So this is a case where both of the powers were odd numbers greater than 1. You could choose either one. You get answers that are equivalent but don't look the same. All right? Okay. So we've dealt with that particular situation, which is that at least one of m and n is odd. So what's left? If at least one is odd, that's case 1. What is not case 1? They're both even, right? That's the only other thing left. If at least one is odd, then sine could be odd or cosine could be odd, or they could both be odd. The only other possibility is that they're both even, right? So this is going to be case 2. So we're back to the original, sine to some power of x, cosine to some power of x. The powers may be the same, they may not be the same, but the powers are both even, 2, 4, 6, 8, 10, etc. So sine to an even power of x, cosine to an even power of x. Again, it doesn't have to be x, but the arguments do need to match, all right? So these types, you need to have the argument matching. This is case 2. Now what we're going to do is that double angle, half angle formula to replace each sine squared with 1/2 times 1 minus cosine of 2x, and each cosine squared with 1/2 times 1 minus cosine of 2x. You might as well go ahead and memorize these. They are super handy. They're going to come up multiple times here in Calculus 2. Just get them memorized. You don't have time to look them up. And if you have to go look them up, then you probably don't know them well enough to think to use them. So you can write them in that form. I prefer this form. This is my go-to form because it works a little bit better in integration. Now, how can you keep them straight? I've memorized personally that they both have a 1/2, so that's not a problem. And I know that it's a 1 plus or minus the cosine of double the angle, so it's the double angle formula. But how do I keep track which one's plus and which one's minus? Cosine is an even function. Remember, it is symmetric with respect to the y-axis. It folds on itself. It's an even function, and I associate even with a plus. Sine is an odd function. Its origin is symmetric. You have to fold down and then across. And so I associate that with a minus, right? So I associate cosine with an even function with the plus, sine an odd function when it graphs with the minus. And that's how I keep it straight, all right? Okay, so what are we going to do? We're going to take these even powers and we're going to convert them so that we're reducing the power. Do you see what that's going to actually do? Instead of being squared, it's going to reduce the power to 1. Now, it does change the argument, but the power comes down to 1. Now, after we've done that, we're going to have to multiply out what we have, and then we may have to do it again, all right? We're going to have to do it again and again and again until we get something that we can integrate along the way, probably with u substitution. And we may have to do it more than once, right? So let's take a look at an example here. This one is sine squared of 5 theta d theta. Now, on this particular one, we only have sine squared. We don't have sine squared and cosine squared. If we had both, then we would have to convert them both if they were both raised to even powers. And then it's more work. Is it doable? Yes, it's just more work, all right? But you can do it. It just takes time and persistence, right? Never give up. So we're going to start with a simple one, sine squared of 5 theta d theta. We have sine to the second power. It has no known antiderivative, so we're going to reduce the power by using that double angle formula. So let's write it again up here. Sine squared of x is equal to 1/2 times 1 minus the cosine of 2x. So whatever the argument is over here on the left, you double it on the right. So if this was 5 theta, doubling it would make it 10 theta, all right? So when we're looking at this, we're going to replace this using the formula. So we're applying a formula. This is an integration technique, so it's really important that you follow this. Follow the pattern. Take what's here, which is 5 theta, and double it, so it becomes 10 theta. So this then becomes the integral of 1/2, 1 minus the cosine of 2 times 5 theta, right? That was my original d theta. And no, if I were doing this for myself, I would not actually write that step out. I would go straight to cosine of 10 theta, d theta. All right, now, what do I do next? Well, distribute the 1/2, all right? Write it as 2 different integrals. So I have the integral of 1/2 d theta, which I can integrate immediately, minus 1/2, and I can pull the 1/2 out, the cosine of 10 theta d theta. Now, you don't have to put parentheses around the argument, at least in my class, but it is good habit to put parentheses around the argument. I'm not always good about it, but I try to remember to do it. This one integrates directly. This just becomes 1/2 theta plus a constant. We'll roll all the constants together. So we have a 1/2 theta plus a c floating around. What about this guy? Well, I can integrate cosine. This is just going to be u substitution, where u is 10 theta. So I've got u equals 10 theta. So du is equal to 10 d theta. But I don't have that. I have d theta, which becomes du over 10. So I can substitute that into the integral, and I get minus 1/2 the integral of cosine of u. I guess I can put parentheses around it, times du divided by 10. Now the 1/10 can come out to the front to join the 1/2, which makes it 1/20. And then I have the integral of cosine of u du. And what is the integral of cosine of u? Yeah, be careful there. You're undoing the derivative. So you're going to come back to sine. It doesn't change the sign from negative to positive. So this stays 1/2 theta. We get minus 1/20 sine of u. And then we've got a plus c. And then remember, you've got to revert back, substitute back into your original, which is 1/20 sine of 10 theta plus your constant of integration, right? And that's your final solution there, okay? So this is a pretty straightforward method. It doesn't seem too particularly hard. It just takes a little bit of persistence and work. Let's take a look at another example, which would be one where we have both sine and cosine, and the argument, again, is not something simple like x. It's 3x, but again, they do match. For this particular case, we still need the arguments to match. Case 3, we'll take a look at where they don't match and some things that we can do there to make those integrate. So I want to convert the sine squareds, and I want to convert the cosine to the 4th. Now, I have to warn you that this is a very unpleasant problem. So prepare yourself for a lot of work, all right? Why? Because that's the 4th power, which means that when you break it down, you're going to have to break it down twice, right? And so it's going to be far less pleasant, and you're going to have some multiplication that you're going to have to do as part of this process. So the first thing I'm going to do is I'm going to rewrite this in pairs. So I have sine squared of 3x times cosine squared of 3x times another cosine squared of 3x. That's what I mean by pairs. I'm breaking them all down into powers of 2 so that I can use the double angle half angle formula to reduce each one individually. So the next thing I want to do, and we'll write our formulas up here in blue so we don't forget them. Sine squared of theta is equal to 1/2 times 1 minus, sorry, that's my dog. No doubt he sees some stranger on the sidewalk, stranger danger. And then we have cosine squared of theta, 1/2 1 plus cosine of 2 theta. Okay, so now we need to individually convert each one of these right here using the formula. So this is going to give me, and this is going to take quite a bit of space. So I have the integral of 1/2 times 1 minus cosine of 2 theta times 1/2 1 plus, oops, not 2 theta. What am I thinking? I'm looking at the wrong thing. I need to double the original argument, which was 3x, so it becomes 6x. And then when I convert cosine squared, I get 1 plus the cosine of double 3x, which becomes 6x. And then I do it again because I've got 2 of the cosine squareds of 3x. So I have a 1/2 1 plus cosine of 6x twice, and then dx at the end. All right, now you may look at this and go, ew, can I split that up? No, you cannot split it up. They're multiplied. Do not split your integral across multiplication or division. Never, ever, ever do that. It's wrong. You can only split across addition or subtraction, and you've got multiplication. Yeah, you've got some addition and subtraction, but they're buried, right? They're not out in the open. You can't split these integrals up. So basically, you've got a 1/2 times a 1/2 times a 1/2. Pull that to the front, you've got a 1/8. Now, we've got this 1/8 at the front, and we have an integral. Now, we're going to have to pick 2 to multiply together. It doesn't matter which 2, but to make it simpler, notice that this is 1 minus the cosine of 6x, and this is the conjugate pattern, 1 plus the cosine of 6x. We like these because they're the difference of 2 squares pattern. So if I take this one here and I multiply it by this one here, I end up with the following. I'll get the difference of 2 squares, which is going to be 1 minus cosine squared of 6x, right? Then I still have this 1 plus cosine of 6x that I haven't multiplied out yet. And my differential is still hanging out over here. It's dx. So this one comes from here, and this comes from there. So we have 1 minus cosine squared of 6x, difference of 2 squares pattern, coming from the product of the conjugate pair. And then this one is just tagging along. Now, what do I have to do? I have to keep multiplying it out. So I'm going to have to multiply this expression by this expression. It's not polynomial because of the trig, but it's polynomial-like. So remember to do the distributive property. 1 times 1 will give me a 1. So this is going to give me 1/8 the integral of 1. And then on the outside, I get 1 times cosine of 6x. So that's cosine of 6x with a plus. And then on the inside, I get negative cosine squared of 6x times 1. So negative cosine squared of 6x times the 1. And then the last, I have a negative times a positive. So it's negative cosine squared of 6x times cosine of 6x means I have cosine cubed of 6x. And it is negative. Maybe I should make these square brackets so I can see. All right. So now I've gotten down to here. Now, once I get to here, what is my next strategy going to be? Well, now it is an integration problem because I've got pluses and minuses that are no longer buried. They're in the main part, right? They're not buried inside the parentheses. They're just in the integrand itself. I guess you could say they're inside the square, but that's just identifying the integrand. So I can split this into 1, 2, 3, 4 different integrals. And that's what I'm going to have to do. So I'm going to split it into 4 different integrals. So go ahead and take a moment and do that. If you want, you can keep the 1/8 on the outside, way at the front. You have the integral of 1 dx plus the integral of cosine of 6x dx minus the integral of cosine squared of 6x dx minus the integral of cosine cubed of 6x dx. All right, so you've split it into all of these different integrals. Now, how are you going to integrate these? You'll notice that this one is really long and really complicated. Yeah, it is, all right? These are not fun ones. These are ones that just go on for a couple of pages probably. The first integral we can integrate directly. It's just going to give us x. The second integral, you need u substitution. U is 6x, du is 6 dx, so dx is du over 6. The third one, remember I warned you, when you have both sine to an even power and cosine to an even power, you may have to apply those double angle, half angle formulas more than once. You got to do the double angle, half angle formula again here. And then we get to the cosine cubed of 6x. Now, how are you going to handle the cosine cubed of 6x? Well, you're going to split it, just like we did in case 1, into cosine squared of 6x times cosine of 6x. Then we're going to convert using the Pythagorean identity on the even pair, and then we'll have cosine of 6x to serve as part of du. So go ahead and pause the integral. Take about 30 minutes, sorry, but that's what it's going to take. And go ahead and integrate each of these, then turn the video back on and we'll compare answers. And I'll color code my answers so you can track each one as we're going from the top to the bottom. Now remember, I said these are pretty nasty, so it's been a while. Let's go back and see what we've got. So we got down to the point here where we had 4 terms inside the integrand separated by plus and minus. We're able to split the integral into 4 different integrals, the whole thing multiplied by 1/8, which I chose to keep on the outside till the very end. Now the integral of 1 dx just integrates directly, and that gives us x. And you'll see that I wrote that way down here in the black color. Now the second integral is the integral of cosine of 6x, which you need u substitution. U is 6x, du is 6 dx, dx is du over 6. You get a 1/6 the integral of cosine of u du, which is 1/6 sine of u, where u is the 6x. And so we end up with 1/6 the sine of 6x, which you'll see down here in the blue color. Now the next one, the third one, is again a cosine squared of 6x. So we're going to use the double angle, half angle formula again to reduce it. That's the formula 1/2 times 1 minus cosine double the argument. If I double 6x, I get 12x. Now this becomes 2 separate integrals itself. So that third one itself splits into 2. And I get minus 1/2 the integral of dx, which is a minus 1/2 x. And then a minus 1/2 the integral of cosine of 12x dx. I need u substitution again. You can see u substitution is coming in multiple times. So u is 12x to u is 12 dx. dx is du over 12. So you get another 1/12 here, cosine of u du. When you integrate, you get minus 1/24 the sine of u. U coming backwards was 12x. And so that gives us a minus 1/2 x minus 1/24 the sine of 12x in this sort of pink magenta color. The third one is a little bit more complicated. Not that the previous weren't complicated. You have cosine cubed of 6x dx. So I did this one in the gray color. So when we come down here to that one, we split it. So again, we have cosine to an odd power, so I split it. Instead of 3, I split it into 2 and 1. And I take the cosine squared, and I use the Pythagorean identity to substitute 1 minus sine squared of 6x. Then I use a u substitution, with u being sine of 6x, and du using the chain rule of 6 cosine of 6x dx. And then that gives me that the cosine of 6x dx is du over 6. So I'm going to get a 1/6 coming out of that particular part. So when I come down here, I end up with 1/6 the integral of u squared minus 1. Now I had a negative on the front, and I converted this to 1 minus u squared, but then I took the negative and distributed it across the integral, which is how I got the u squared minus 1. When we're done, we're left with 1/18 u cubed minus 1/6 u, yes, with a plus c, but we have plus c's on all of these integrals, so we're going to roll them all together into one great big plus c. Going backwards to our u, coming up here, it was sine of 6x. So we have 1/18 sine cubed of 6x minus 1/6 sine of 6x. And then we can stick the plus c on the end of it. Now we can distribute the 1/8, or you could have combined it and then distributed the 1/8. You'll see I've color-coded that you have like terms in yellow and like terms in blue. I've highlighted these here. The ones in blue cancel and knock each other out. 1/8x is 2/16 minus 1/16 gives us 1/16 x. And then we have the remaining two terms plus c. It's doable, but it's long. It's long and it's complicated, and you have to keep track of each individual part. I highly recommend using blank paper and different colored pens to keep track of each individual integral that you're working on. Let's now take a look at case 3. Case 3 is the last one we have left. This is where both m and n are positive 1. So we've dealt with powers greater than 1, where 1 at least was odd, and then where they were both even. And now we want to look at this last case 3, where the powers on sine and cosine are 1, but in this particular case, the arguments don't match. All right, so they don't both have the same argument. So when we're looking at one like this, what we basically want to use is we want to use this trigonometry formulas for the sum and difference formulas, and also the product formulas in order to solve these. Now, my classroom, I do not expect my students to have these memorized. I don't have them memorized. I've never, I don't think, had them memorized except maybe once when I was doing a lot of trig. They just don't stick with me because I don't use them very often. But when I need them, I know they exist and I go and get them. That's kind of what I expect from my students. So when we're looking at these, this would be types 1, 2, and 3, where in type 1, we have sine of ax times cosine of bx. Notice that the power on sine and cosine is a 1, and a doesn't equal b. So this could be sine of 2x cosine of 5x. 2x and 5x don't match, so the arguments do not match. In something like this, we want to use this formula right here that you see off to the right. It's just a Pythagorean, or just a trigonometry formula from trig, in order to make it into something that we can integrate. So it will end up over here. So you'll have an integral of 2 separate sine functions. And then, of course, you can integrate those, because you can integrate sine, you get negative cosine of x. And you can substitute doing u substitution, all right? So this is a somewhat simpler one in the sense that there's not as much work as on some of the ones we've seen previously, but it does require a formula that you're probably never going to get memorized. So you're just going to have to know to go find the formula and use it when you need it. These won't come up in our homework too terribly often. Now, this was a product of sine and cosine where the arguments didn't match. So sine and cosine where the arguments didn't match. What other options are there? Well, I could have sine times sine where the arguments don't match. So that would be type 2. I've got a sine of ax and a sine of bx, and a and b don't match. So this could be something like sine of 2x times the sine of 5x. 2x and 5x don't match. I can't combine them. They're different. So I use, again, this sum and difference formula that you see right here, which will convert that product into the difference of two cosine functions. And then I can split the integral across the two, and I can integrate each cosine function using u substitution. So that's basically pretty straightforward. Of course, if a and b were the same, then it would be sine squared of that, and then I'd use the reduction formula. So it's not really a case 3 type. The last option is that they're both cosine, where the arguments do not match. A does not equal b. And we also have a formula for this one, which will convert it into the sum of two cosine functions with different arguments. And then you can use u substitution in order to integrate each of those. We're only going to do one of these because, like I said, they don't come up very often. And it's not one of the ones that I expect my students to have memorized. I'm mostly focused on the others where you're using either the double angle and half angle to reduce sine squared or cosine squared, or where you're using the Pythagorean identity to substitute to lead to an integral that you can use u substitution or direct integration. So let's now take a look at this example. We have sine of 3x times cosine of 5x. So we have sine times cosine, and the arguments don't match. Now, if they did match, I could just directly do u substitution, right? Because the derivative of sine is cosine, so I wouldn't need any of this. But they don't match, so I do need this. So I've got a sine and a cosine. So we want to come back up here, and I believe this was type 1, where we have sine and cosine, and we have this formula right here. So I'm going to copy this formula, and we'll see if this hopefully doesn't freak out my computer. Sometimes when I try to copy these formulas, when I'm writing on here, it kind of freaks it out a little bit. Okay, so I've got that there. Tab over a little bit, paste the formula. Okay, so let's see how to apply the formula. Applying patterns is hugely important in mathematics. It's one of, well, it's really what math is all about, right? Math is about patterns and predicting things. It's all about pattern matching. So we want to take sine of alpha cosine beta. So alpha is the argument to sine, and beta is the argument to cosine. So alpha is 3x and beta is 5x. So you might want to go ahead and write that down somewhere. So alpha is equal to 3x and beta is equal to 5x. So you're going to take the integral of the sine of 3x, and yes, I should have parentheses around those, and the cosine of 5x times dx. And again, this is multiplication in the product, but it's the same type function. So integration by parts is not an option. And then we're going to rewrite this as 1/2 times that whole thing. So I'm going to pull the 1/2 out. And then I have the sine of alpha minus beta. So alpha minus beta is 3x minus 5x, which is a negative 2x. And then I have plus, and this is the argument or the integrand, the sine of alpha plus beta, which is going to be 3x plus 5x, which would give me 8x. And then the differential is dx, right? Everybody with me so far? Pause the video if you need to and think about the formula. Now, what I need in order to integrate this is I need to think about the sine function. Sine is an odd function, so sine of a negative angle is negative the sine of the angle. So the sine of negative 2x is negative sine of 2x. So it's we're not factoring out the negative. That's not a thing. It's an odd function, which means that's just the way it works. If it were cosine and there were a negative, then the cosine of negative 2x is the same as the cosine of 2x because it's y-axis symmetric. So we have to think about whether the function's even or odd. So then we're going to rewrite this as negative 1/2 the integral of sine of 2x dx. And then I'm going to distribute the 1/2, and I get plus 1/2 the integral of sine of 8x dx. Now this is a pretty straightforward integral. At this point, there's not a whole lot to do except use substitution on each one. So we'll do the use substitution and we'll integrate and come up to an answer. So go ahead and pause the video, work it out on your own, and then turn it back on and compare your answer to mine. Okay, let's see what you've got. So we split it into these two different integrals. Each one needs its own u substitution, not the same u. U on the left one is 2x, so du is 2 dx, dx is du over 2. When you make the substitution and integrate, then you're going to have a minus 1/2 times the 1/2 from the du over 2, sine of u du. Now the integral of sine of u is negative cosine, but you've got a negative here, so a double negative makes it positive, and then we replace u with the 2x. Then we have to repeat this process using u substitution on the second integral, but the second integral, u is 8x, so du is 8 dx, dx is du over 8. So we get a 1/2 times a 1/8, the integral of sine of u, which turns out to be negative cosine of u. So we end up with a negative 1/16 cosine of u, and then we back substitute that u is 8x. All right, so we finally reached the end of this first set of trig integrals. We've taken all the different cases that we can think of for an integrand where sine and cosine are multiplied together. In the first two cases, the arguments were the same. And in the second or third case, rather, the arguments were different. So we've looked at different ways of integrating the product of sine and cosine. In the next video, we'll be taking a look at integrating products of tangent and secant. I hope you'll join me there.